Welcome to the proof of Rolle's theorem. So just a quick reminder, Rolle's theorem statement says if f is continuous on the closed interval AB and differentiable on the open interval AB, and f of A equals f of B, then there exists some C in the open interval AB such that f prime of C equals 0. So for our proof, again, we're going to assume that these conditions are met. So suppose f is continuous on closed interval AB, differentiable on the open interval AB, and f of A equals f of B. Then we're going to divide this in two cases. So case 1, suppose f is constant on the closed interval AB. So in other words, suppose that f of A equals f of x equals f of B for all x in AB. Well, by default, constant functions have derivative 0, right? So then f prime of x equals 0 for all x in AB, open interval. And so we could pick any value of C, right? So we can pick any C in the open interval AB. Case 2, we're going to assume the function is not constant. So suppose f is not constant on the closed interval AB. Then what we have is that f of x is either greater than f of A or f of x is less than f of A somewhere in that interval. Right, so here's some values of x. In the open interval AB. Right? If that were not true, then it would be a constant function. Now, by the extreme value theorem, right, by the extreme value theorem, we know that there has to be an absolute minimum and an absolute maximum on the interval, closed interval AB. So there must be an absolute minimum and an absolute maximum. On the closed interval AB. Again, the extreme value theorem says if the function is continuous on the closed interval AB, then it must have an absolute minimum and an absolute maximum on that interval. Right. Furthermore, since there are some values of x where f of x is either larger than f of a or smaller than f of a, at least one of the absolute maximum or absolute minimum must occur inside the interval. So basically we know f of a equals f of b cannot be both the absolute maximum and the absolute minimum. So at least one of the extrema falls at some x equals c with c in the open interval AB. We also know that extrema can only occur at either an endpoint, which this is not, or at a critical value. So extrema of a continuous function must occur at an endpoint or at a critical value. Since C is not an endpoint, x equals C must be a critical value. And since critical values occur either where f prime is 0 or f prime is undefined, since our function f is differentiable at x equals c, f prime of c must equal 0. So we know that f is differentiable at x equals c. So f prime of c exists. Therefore, it must be equal to 0. So therefore, f prime of c equals 0, since x equals c is a critical value. So we have shown when the function is constant, we can pick basically any x x equals c. And when the function is not constant, it has to have either an absolute max or an absolute min that occurs somewhere in the middle. And we will pick that x value as our target desired point. You may have more than one place, but we're guaranteed at least one place.